So moving on to our next presentation from Nicole and also from Kirill as well. And this is Pipebots. So this is another fascinating one. Every time I go along to conferences and things like that, and they do those kind of networks, they do those kind of workshop sessions on how to solve leakage, I generally time it until someone says robots in pipes. But here we are, robots in pipes. Nicole, Kirill, over to you two.
Thank you very much, Jez, and welcome to this presentation. So it's so my name is Nicole Mitya. We've also got Professor Kirill Horoshenkov on the call. That's the University of Birmingham and Sheffield represented, but there are other universities involved in the project, as you can see at the bottom. Just to give you a bit of an idea, what is Pipebots and what's the aim? So really, the aim is to design micros, so it's very small robots, swarms of robots, to go into our underground pipe networks and to live in our underground pipe networks. And really the idea is to revolutionize the buried pipe infrastructure management, because these robots are there permanently or semi-permanently. They communicate while they're in the pipe, they charge while they're in the pipe, and they basically just live there. And ultimately the vision is that they could also actually do repairs. So as you can see, this is a sort of research project. It's funded by the Engineering and Physical Science Research Council. It's what's called a program grant, which means we've got quite a long time to do this work. So it's a 5-year project, started in 2019 and is due to finish in 2024. It does involve 4 academic institutions, as I said, 2 represented on this call today and in the conference. But it's got over 40 researchers working on that problem, with well over 30 industry partners. And we don't just look inwardly, we also look outwardly. And that's not just in the UK, but that's also overseas. So we're also working with our international partners as well. So what are we actually trying to do? So really, what we're trying to do is develop some new science, specifically on the sensing aspect. So the project, you can't quite see this because it's quite small, I bet, on your screen, but you can see a bigger version on the website. So the project is split into 8 themes, where 5 of the themes really look at the technology element, and 6 of the themes look at the technology aspects, and 2 of the themes look at broader issues, which I will go into in a bit. But it's really trying to combine advances in robotics, advances in navigation, and advances in communication to come up with a solution that works for the quite challenging subsurface infrastructure networks and the environment down there. So the aim is to advance this from the laboratory prototype to field scales. Some of you may know that a lot of the UK universities had some funding through something called UCRIC or UK CRIC, which stands for UK Collaboratorium for Research on Infrastructure and Cities. And as part of this, both Birmingham and Sheffield have some big laboratories built where we can actually do near full-scale experiments. Clearly, we can't make it as complex as in the real world, but we can actually try quite a few things out. One of the key aspects of the work that we're trying to do is to actively engage with our end user community. And as Jess already mentioned, he's been to some of those events, and I'm sure some others of you who've on the call have been to some of our events. If you haven't, we've got a website, we've got contacts, which are on my final slide. So please do get in touch if you haven't heard about it or want to find out a bit more. I should say that it wasn't just a whole bunch of academics sitting in a room who dreamed up this project. We actually held what's called co-creation events, co-creation workshops to really derive the research. And really what we're aiming to do ultimately is to develop a world-leading research center of autonomous sensing for buried infrastructure. One of the things we're doing is we're going through a number of sprints, and a sprint in our case means something where we work on a specific problem for a very short period of time. And one of these problems was, can we actually, in say something like 4 to 6 weeks, can we actually develop a sprint robot? So in that very short time, can we develop a prototype robot that can actually function and do a few certain things? So we were successful, and what I'll show you now is a short video of our sprint bot. So you can see our sprint bot at the end of a pipe, a drainage pipe. trying to find its way in. It's moving along, so it's not just a robot that was moving along, it also had some sensors on it, was sensing something. It's ending up in a manhole, and it's successfully actually finding its way to the next outlet. You might wonder what these springs are at the end, so at the tail here and at the other end, that's so in case it falls over, it can right itself. So that's quite important for us. And there it goes again. As you can probably see from the pictures, this was clearly somewhere above ground. So this was a very simple network that we put up above ground. But what are the lessons that we learned from there? So there were a few lessons that I share with you. And as you might have already seen from the dimensions or had some guess from the dimensions of the sprint bot, it's rather large, but it fits successfully in 300 millimeter and 240 millimeter diameter pipes. At the 210, it's struggling a bit, as you can see on the image. It can successfully handle T and Y sections and get in and out of manholes. It was clearly a very simple robot, and that's really the aim of these sprints, is really to come up with a very quick, maybe quick and dirty solutions, but to get the whole team working together towards something. The robot was controlled using a simple app on a mobile phone, as you can see at the bottom. It successfully integrated the electronic systems, and it actually integrated the sensors. And one of the lessons that we learned is that a modular system is really successful because, or has advantages, because we can switch things in and out as we develop them further. So that was quite an interesting lesson learned. I appreciate this is a very quick overview of what we're doing. So one of the other aspects that we are doing is, these are themes 7 and 8, is to look at emerging science and systems and use system knowledge, and also end user engagement. And really what this is trying to do is to not just look at the technology that's important, but also to understand and map the dynamically evolving infrastructure and urban systems with which it interacts. So it's not just looking at the buried pipe infrastructure in isolation. Clearly, it's also trying to horizon scan and look at other technologies that emerge, not just from the buried infrastructure management, but also others. But it's also looking at the political, economic, and social environment, and make sure that whatever we develop actually seamlessly integrates into practice. So that might mean changes in business cases, or considering alternative business cases. That might be looking at regulations. The other thing that we are looking in that aspect is to support the testing, the validation and demonstration of new sensing and inspection technologies at full scale in realistic environments. So if we can create a test facility where the likes of the presentation we've just seen, where people can come and test and we can evaluate different systems against each other. We're also trying to develop algorithms to synthesize collected inspection data. So it's one thing, obviously, getting the data, but it's also the making sense of the data. And also, finally, ensure that autonomous robotic inspection technologies are adopted so that they can really lead to a step change reduction, asset failure, and loss of service. So one of the things I was asked to mention is, what are the challenges? And I'm sure this doesn't come as a surprise to most of you. One of the challenges is clearly the miniaturization of the robot, so making it small so that it can actually go into your 100 millimeter or even 50 millimeter pipelines. It's the communication and data retrieval, because we know that communicating through RF, through the ground, is quite difficult. So radio frequency signals through the ground is really difficult. So how do we get the data out? But these robots, so we've seen some examples of tethered robots. We are trying to have autonomy in our robots and have automatic navigation. We want to ensure that there's no impact on the flow, but also we're not just looking at potable water, we're also looking at drainage and sewer systems. So therefore it often has to operate in wet, dry interfaces. So where you've got water at the bottom and dry at the top. But it also has to be
2 minutes, Nicole.
Yeah, agile to cope with the mobility within, agile to cope with the different networks. And finally, before I get to my last slide, we identified 4 case studies. These are the ones we're working on the most, what the robots are aimed at. That's blockage, asset management, asset mapping, condition assessment, and as a subset, there's leakage. And finally, coming up, I've already mentioned this, there's clearly a big opportunity for collaboration. There are lots of things that we need your help with. If you've got any questions or want to find out more, have a look at the website or send us an email. Thank you very much.
Thank you, Nicole. Great presentation. And yeah, really interesting to see how that one's developing. So I think, yeah, it's really interesting that you finished with the challenges, and it was great to see where you've got to. So let's talk through some of those ones. And firstly, the obvious one, I think, to everybody sitting here is the challenge of introducing that into clean water environments. How do you feel that will go?
Well, I think, I mean, there are some existing regulations out there, and I guess being a research project, while we're keeping that in mind, it's not our main focus of the work. We want to have a proof of concept that we can have a swarm of these mini robots in our pipe system, and therefore they can operate autonomously in there. But what we're doing is we're investigating what materials we're using, and so to ultimately get them into our systems.
And that kind of leads neatly into the second bit there. You just talked about robot swarms, and that's one of the really interesting applications, I think, is the idea that you could have multiple robots going past the same point. You get a lot of additional information from that. Is that correct?
That's correct. And the idea is also that maybe we have got robots that perform slightly different tasks and they communicate with each other. So it might be that a robot has a certain sensor on it, indicates a problem, communicates that to a different robot. That robot might actually go to that particular point, investigates it a bit further, or with other sensing technologies to get a bit more information. So it's not just a duplication, it's also maybe utilizing different specifications for the individual robots.
Thank you very much, Nicole. Excellent.